Okay, so welcome to this next video in the playlist on probability. In this video what we're going to do is tackle a problem in conditional expectation, and this is quite a difficult problem, but probability actually makes it easier, and in particular what we're going to use is a linearity of the expected value. Okay, so this is the problem. You have, let's say you have 100 people, and then you have 15 committees, okay? Right? And then you have each person of these 100 people is on 3 committees. So each person chooses 3 committees to be on. So overall, the number of people, well, if you add up, if we drew out all the committees, so if we drew out the committee here, the committee here, the committee here, etc., and we went all the way up to the 15th committee, and you put in the 100 people into the committees that they're in, then the number of people you count up, if you counted them all separately, i.e. you counted each person 3 times because he appears in 3 committees, or he or she. So let's say this is person 1, he's going to appear in 3 committees, so let's say he appears in committee 1, committee 3 and committee 15, then he'll get counted 3 times. So overall, if we count up all the people in here, add it to all the people in here, or add it to all the people in here, etc., we're going to have 300 people. But of course, there's only 100 people, it's just that they appear 3 times. So each person is on 3 committees, so I'll just put 3 committees. Right? Okay. So how many people are on, well, we're also going to assume, sorry, I didn't say this, we're also going to assume that there's an equal number of people on each committee. So, if there's 15 committees, then if we divide 300 by 15, then that's going to give us 20. So that's going to give us 20 people on each committee. So there's 300, if we count up all the people in here, we know there's going to be 300 from the fact that there are 3 committees. But that doesn't tell us how many there are on each committee. But I'm going to tell you that it's equal, basically. So there's 20 people on each committee. Okay, so if we imagine every single person having a different number, so you have person 1 here, so this is person 1, and you go all the way down to person 100. There are absolutely loads of different ways you could ascribe these 100 people into these 15 committees, such that every person is on 3 committees and every committee has 20 people in. Now, the problem we want to tackle is we want to prove, this is what we want to prove that at least one of the intersections of these 2 committees. So there exists, right, so we can intersect these two committees if these are sets, basically. What we want to say is, let's say if we intersect committee 1 with committee 2, what that means is how many people are, which people that are in committee 1 are also in committee 2. So if I write 1 intersection 2, that means the people that are in committee 1 and committee 2, etc. What we want to show is that there is at least one of these intersections. So there is at least one intersection of the committees, So you choose 2 arbitrary committees from the 15. So let's say committee I here and committee J here. So you pick 2 committees, and basically there will exist some combination of committees that you can pick such that there are 3 people in the intersection. There is at least one intersection of the committees which contains 3 people. That's what we want to prove. And that works no matter how you choose to ascribe these 100 people into these 15 committees, such that every person is in at least 3 committees and each committee only has 20 people on. So, what we're trying to prove is that there is, for whatever way you do that, there will always be, you can never ever avoid the situation that 2 of the committees of the 15 will share 3 people, i.e. 3 people will be on both one committee and the other committee for some choice of the 2 committees from the 15. That's what we want to prove. Okay, and the way we're going to do it is we're going to use probability. So let me explain how we're going to do it. Our great big probability space has got 2 sorts of dimensions, if you like. The first way we can split up the probability space is every possible way. So we'll draw the 15 committees in here. 1, 2, 3, ... 15, all the way up to 15. And in this probability space here, in this sample space, I'm going to put in every possible way there is of ascribing these 100 people which we are all viewing as distinct, i.e. these people have all carried a label. They've all got labels 1, 2, 3. So imagine them all holding up signs. So this person's got a sign saying 1, this person's got a sign saying 100. So all of the people are distinct. And basically, we are looking at all the different ways that you can ascribe these 100 people into these 15 committees, such that every committee has 20 people in, and every person is on 3 committees. Okay. Right. If we put person 1 in committee 1, and person 1 in committee 3, and person 1 in committee 15, then there are obviously loads of different possible ways of doing this, which fix that person in those 3 committees, because all the other 99 people can go into it can all be rearranged. But basically, what I'm counting as different is if I bring person 1 over here, that will be now different. That however you ascribe the other 99 people, that will be a different way of doing this, basically. So I am viewing the people as distinct. I'm not just caring only about how many people there are in each one. I am viewing the people as distinct, okay? So if I say swapped person 1 and person 2 around from one committee to the other, that would be counted as a different scenario in here, even though the number of people, yes, it has to be that way, because the number of people is always going to be fixed. There's always going to be 20 people here, 20 people here, 20 people here, etc. So that's how we are finding these different ways of doing that. Okay, so in this probability space, I want you to put in every possible different way there is of ascribing these 100 people into these 15 committees, such that every person appears 3 times, and in each committee there are 20 people. So there are absolutely loads of ways of doing that. And I'm putting them all in this great big probability space. So here is another way of doing that, etc. And you could go on. Right, now I'm going to change the way I store all this information now, and this is a big thing to understand. So if I want to specify how I have ascribed the people into these 15 committees, then I could just tell you, as I have done, which people are in each committee. But another way I could do it, and a way that's potentially more useful, considering what we're trying to prove, is to list all of the possible intersections and tell you which people are in those intersections, basically. So, how many possible intersections are there? That's just how many ways are there of picking 2 committees from 15. So there's going to be the intersection 1, intersection 2, 1, intersection 3, 1, intersection 4, etc. all the way up to 1, intersection 15. Then you're going to have 2 intersect 3, 2 intersect 4, 2 intersect, etc., 2 intersect all the way up to 15. So the total number of ways, the total number of committees there are going to be is how many ways are there of picking the first committee that's going to be in the intersection, which is that there are 15 ways of picking your first committee that's going to be in the intersection. So you could pick 1, 2, 3, etc. And then how many ways are there of picking the second committee? That's going to be 14. But that overall is going to count the 2 different orders of picking them as separate. So if I picked 1 and then 2 as my second one, it will count that as different from picking 2 and then 1. But of course the intersection of 1 with 2 is the same as the intersection of 2 with 1. So I don't want to do that, so I have to divide by 2. So this is the number of ways of picking 2 committees from the 15, and that therefore is the number of possible intersections of the 2 committees. I.e., if we that's the total number of ways you can pick two committees, and what other intersections are possible. If you have an intersection, it's got to be an intersection between two things. It doesn't matter which order you pick them in. So that's the number of total intersections there are. Now, if I instead sort of list off these intersections, so I start off with 1 intersect 2, 1 intersect 3, 1 intersect 4, etc. And I tell you for absolutely every single intersection, so I go on and on, I do all 15 times 14 divided by 2 of them, whatever that number is, so let's try and work that out. So 2 and 14 cancel to make 7, so it's 15 times 7, which is 70, 105. Okay, so that's the total number of intersections. So if I tell you which people are in each of these intersections, then I can know instantly, I have exactly all the information that's here. In fact, I have some degenerate information in here, because once you've told me 2 of the intersections that person 1 is in, I instantly know what the 3rd intersection is. So for instance, if you tell me that person 1, in this case, person 1 is going to be in the intersection of 1 and 3, because he's in both 1 and... well, he was in 1 and 3. Sorry, we've now moved him into... oh, yes, get him out of there. Put him back in 3. Okay, so we've got person 1 in committee 1, committee 3, and committee 15. Then if I convert this information here into this form over here, then I'm going to have person 1 in this intersection between 1 and 3, so he's going to be there. He's also going to be in the intersection of 1 and 15, because he's in both 1 and 15, so he's going to be here as well. And finally, I know instantly the final intersection he has to be in, because he's in 1 intersect 3, which implies that he's in 1 and he's in 3. He's in 1 and 15, so that implies he's in 1 and 15. He's only in 3 committees, so now I know all 3 committees that he's in, so I know instantly also that he's in 3 intersect 15. That's what I mean by degenerate information. Once you know 2 of them, the two of the things that he's in, you know the final one that he's in. Whereas in this case, if you know 2 of them, you don't know what the final one he was in was. Okay, so basically what I hope I've convinced you there is, if I know all of this information, I can go back to knowing this information, because if I know what intersections you're in, if you're in an intersection, it implies you're in both of the committees that form that intersection. So I know 2 committees you're in instantly, then I just need some more information. If you're in 3 committees, then you're going to be in total in 3 intersections. I actually only need to know 2 of them to work out which 3 committees you're in. So basically, if I know all of this information, if I know where every single person from person 1 to person 100 is you put person 1 to person 100 in 3 of these circles, then I can go back and get this information. So another way of storing the information of how we've ascribed these 100 people into these 15 committees is to ascribe the to store it in this way. So to ascribe the 100 people into these committees down here, basically. Sorry, these intersections of committees. Of course, you have to be slightly more careful now, because you only have free will with 2 of them. So you pick 1 that he goes into, you pick 2 that he goes into, and then the 3rd one's determined. So it's even more complicated to actually work out a plausible way of ascribing 100 people into this than it is to work out a plausible way of ascribing 100 people into this. Okay, right, but however, the point is that I can transform the information in this, the storage of this information here, which was committee-wise, so this was telling you committee 1, 2, 3, all the way up to 15. Now what I want to do is I want to change the way I look at this. So let's cut off this probability space here, so get rid of that, and we'll draw the transformed probability space over here. So I'm just storing the information of these outcomes here in a different way. So now I'm going to have each outcome stored in the way of intersections. So we've got 1 intersect 2 here, 1 intersect 3, etc. So we've got exactly the same, all the same possible ways of ascribing 100 people. In here, though, are also in here. They're just stored. The information is just stored in a different and a way that's going to be more amenable to us being able to show this way. So here we've got 1 intersect 2 again, 1 intersect 3. Okay, So what we want to prove, we want to prove that there is at least one intersection of the committees which contains 3 people. So in this probability space, there are all these possible ways of ascribing these 100 people into these 15 committees, stored in this way of, we know, where you tell me instantly how many people, which people are in each intersection, basically. What I want to prove is that for every single possible way you can do this, for every single possible way, for every single possible outcome in this probability space, one of these intersections, so if I go along this and look at these, how many did we agree? There's 105 balls in here. If I look in all of these 105 balls, one of them, in absolutely every single case, one of them will have at least 3 people in. That's what I want to prove. Right, so we'll continue with that in the next video.